Hi everyone, my name is Emmanuel. I'm going to present to you my project. My project is about the semantic relatedness with transformer models. In specific, I'm going to talk about the SBERT approach. So the first thing which you need to understand, we need to understand what we mean by semantic relatedness. And this is just a measure, or it measures how closely words or phrases are connected in meaning, encompassing relationship beyond direct synonyms, like thematic connections. The research problem of this project is that traditional approaches, for example, the word net, are limited in general semantic understanding, focusing more on synonyms and failing in broader context. So the project goal is to develop a robust model using model transformer techniques to accurately predict semantic relatedness for enhanced language understanding in natural language processing. There are some traditional approaches which were developed for semantic relatedness applications. And this includes lexical resources, where the WordNet and others, they measure semantic similarities by distance in taxonomies, but struggle with non-synonymic relationships. We also have the distributional methods, and find that the co-occurrence data, they capture the context, but they lack in-depth understanding of complex relationships. So the transformer models, they came to solve these problems. And transformer models came with the introduction of models like the BERT, which enabled deep bidirectional context modeling. However, the BERT model is not the best solution for this project. So I'm going to use the SBERT. This is because the BERT model is computationally expensive and it requires more computing resources. So I had to adapt to the SBERT model. So the SBERT model, which I'm talking about, it adapts the BERT specifically for sentence embeddings, allowing efficient and scalable similarity computations ideal for semantic relatedness. As I said earlier on, the goal of this project is to train and fine-tune the model on the SimReal 2024 dataset. And this is done to achieve a high alignment with human judgment on relatedness. I'm going to talk about the SBERT architecture here, whereby this project, or the SBERT, it uses the CMS network design, which processes sentences in pairs, in parallel, creating embeddings to compare via the cosine similarity. And this design is efficient, reducing computational demands compared to traditional BERT, as I said earlier on, while retaining semantic accuracy. The training process of this project involves the use of the cosine similarity loss, which measures the angle between sentence embeddings to quantify the relatedness. It also involves optimization, whereby the training is conducted over 3 epochs with learning rate of 2 to the exponent of -5. And this was chosen to balance convergence and performance. The tools used for the project are the sentence transformer libraries for training and fine-tuning. I'm moving on to the results and the evaluation of the model. So, with regard to the results, I'm going to start by talking about the training loss over the epochs, where we have this diagram which illustrates the diminishing of the training loss steadily over the 3 epochs. And we can see that there's a noticeable diminishing loss over the 3 epochs. This is from 0.0136 to 0.0029. And this shows effective learning rate and convergence. We can also see that there's a smooth decline in the loss, And this suggests an optimal learning rate and stability without overfitting of the model. The model was evaluated using certain metrics, that is the Pearson correlation and the Spearman correlation. And this was done on the dev set and the test set, whereby the dev set is the development set of data, and the test set is the data set used for testing. So on the dev set, you can see that the Pearson correlation is 0.812, and the Spearman correlation is 0.816. And this demonstrates strong alignment with relatedness. On the test data set, the Pearson value is 0.836, and the Spearman correlation value is 0.825. And this confirms that the model generalizes well to new data, that is the unseen data. In conclusion, we can see that the model demonstrates both accuracy and scalability, making it viable for real-world applications. However, this model can also be enhanced to suit general purpose applications, where, for example, we can incorporate knowledge graphs. And this enhanced model understanding of specialized domains like healthcare and legal through models like KBERT. We can also enhance this model in terms of the broader application, whereby extending the model to cross-lingual semantic similarity for translation and question answering in multilingual settings. And if we can, or if the future researcher can work on this, the model can be well enhanced to suit more complicated tasks. Thank you.